engineering professional and a consultant with over 25 years of teaching, research and professional experience, not in Sri Lanka, but also in countries such as United Kingdom, Canada and New Zealand. Dr. Lucas has contributed vastly for the development of the field of engineering. He has received many awards and honors in recognition of his contributions, including multiple Research Excellence Award from University of Moratuwa, Best Paper Awards, Fellowship and Emeritus Professorship from University of Moratuwa. Over to you, sir.
Followed by 10 minutes of question and answer. So we will have a question and answer immediately after the presentation because it's easier for people to remember and ask questions. The 4 presentations are on various topics. First one is UAV-based green ultra network and 5G communication. Next one, unlocking space access for mankind, reaction engines, and the Sabre propulsion system. The next one is design and application of smart piezoelectric devices. And the final one is structural design of robotics. Now I will go on to the first paper. UAV-based green ultra-dense network and 5G communication by Professor Nalin Jayakody. Professor Nalin Jayakody received the PhD in electronic, electrical and communication engineering from the University College Dublin, Ireland in 2014. He received MSc degree in electronic and communication engineering from the Department of Electrical and Electronic Engineering, Eastern Michigan University in 2010. And BE electronic engineering degree with first class honors in 2008 from Dublin University of Engineering and Technology, Pakistan. From 2014 to 2016, he was a postdoc research fellow at the Institute of Computer Science, University of Dublin, Estonia, and Department of Informatics, University of Bergen, Norway. From 2016, he was a professor at the School of Computer Science and Robotics, National Research, Tomsk, Polytechnic University, Russia. Professor Jayakody also serves as the head of Research and Education Center on Automation and Information Technologies. He spent a short research stay at Center for Telecom and Research, University of Sydney, Australia in 2015. Professor Jayakody currently serves as Director, School of Postgraduate Studies and Research, Sri Lanka Technology Campus, Sri Lanka. Over to you.
Thank you. Alright, so distinguished guests and all the attendees. So first, thank you very much for inviting me over for Deputy Vice Rector of Vice Chancellor of Sir John Fathalala University, and also Mr. Gunasiya, HOD of Electronics Engineering Department, and also my postgraduate student Somali Moratuwa for extending an invitation to be here today. So it is such a privilege to be here. I have been telling to all the members that I met, the event is really nicely organized. So let us talk about what is my topic today. I slightly changed the topic because I was informed the audience is more general on the engineering side. So my topic is UAV-based green 5G communication. So I will present talk in a way that it will be more accessible for all of you. So don't worry, I presented it to my mom and she said she understood. Okay. So generally I probably you have came across the keyword of 5G, and I'm sure it is known to you by now. So it is in everywhere. If you go to Google and if you look at the newspaper, So everybody talks about 5G. And what is this 5G? So let me bring along the storyline, what is 5G? So the first, as you might remember, in 1980s, in the world we developed analog voice, but in the first G or the first generation communication. However, I think it came to Sri Lanka in early 90s, but in the world it was developed in the 80s. So, and then in the second generation, we introduced voice and the SMS plus marginally emails. So that was in 1990s. I heard that it was implemented in Sri Lanka in the mid-90s. And then in the 2000, mobile internet and the positioning was taken place. And I think more of us are now familiar with what is 3G because you get this internet in the mobile phones. And in 2010, fourth generation was implemented. So with the 4G, one of the groundbreaking technology was LTE Advanced. And there is a kind of a it's not misunderstanding, but misagreement between the companies as well as scientists. As scientists, we always look for IMT 4G and IMT 2010, IMT 2020, right? But the mobile operators, they like to call this very fancy word of 5G, which is not the level exactly what we are looking at the level, when it comes to the IEEE 2020. So what is 5G? 5G is not an evolution of 4G communication. It is a new mobile communication system. So we should not understand it as the next step going forward from 4th generation. So this will be a new mobile experience and it is for everyone, everywhere. So I mean, in my next slides, I'll explain a little bit technically what that really means. So the 5G comes with three main keywords: EMBB, Enhanced Mobile Broadband. There will be a high availability of the bandwidth. So probably you know the most expensive real estate in the world is the bandwidth. So I mean, I'm coming from Sri Lanka Technological Campus, which is a subsidiary of Sri Lanka Telecom. So we always hear how much bandwidth is expensive, how much million of dollars they need to invest on the government to get the bandwidth. Now, as when the 5G comes into play, it is expected that 2.5 billion connected devices will be there in a couple of years' time, and 30 billion connected devices will be in play in 2025. So everyone will have 3 to 4 devices to connect. So you are connecting, everyone is connecting everywhere. So a person in Colombo will have the same privilege and access to the same information as a person in Moratuwa or somebody from Mimuri. So then, through the 5G technology, what we are trying to improve is the user experience. And everyone will have same access to the same information. It's one of the ways I'm just presenting the way you can understand. So the access to information is one of the human rights now in the new world. So in the past, there were 4 basic requisites as standard as the human right, but with the new innovation world, information is one of the human rights. So the 5G making it accessible and available for people. So there are a lot of, by 2020, we are expected to have 1.5 GB traffic per day and 4 terabyte of data per day and 5 GB of data of connected airplanes. And 5G also supports smart factories. I'm not sure whether you heard the word smart factories. Today at the keynote, I think the speaker mentioned about Industry 4. Industry 4 is the next generation of automated industry. So that means we embedded artificial intelligence into it. So when there is artificial intelligence is placed with automation, we call, actually it is born in Europe, especially in Germany, we call it Industry 4. So even Industry 4 requires 5G to make it a reality. So the 5G will make the Industry 4 and Internet of Things a realistic practice, because we need high speed, we need low latency communication, and it should support large number of connected devices. So with the 5G, so one is eMBB, other one is MMTC, massive machine type connected devices. And the third one is URLLC, that means ultra reliable low latency communication. So they are very important. Ultra reliable low latency communication will support robotic surgeries. Because let's say we are doing a surgery at KDU hospital and you need an expert support from somebody in Europe, right? And if there is a delay in between, so how the expert support can be useful, right? When somebody say, okay, they cut the arteries and then like maybe patient is dead because instruction was delayed. And so with the 5G, we bring down to the KPI or key performance indicator to 2 millisecond delay. So then, as I said, robotic surgeries and the distance communication will be realistic. And that also supports connected cities. It is one of the new topics in the world to talk about ITS, Intelligent Transport System, because we need to connect cities. And how we realize the connected cities, it is by means of communication. So we have to have a strong communication platform to develop this connected cities concept. So this is another slide on the 5G for everyone. So that enhance the foundation and that connect everything and new ways of interacting, because now everyone is on social media, right? So everyone is connected in one way or another with the society. And then, so we also believe that with the 5G that it support the smart factories, and factory will be more smart, and the 5G will support it. There is a European project called Clear 5G, and that is the main source of knowledge where emerged the idea of clear knowledge, the smart factories. So evolution of 5G, actually when it thinks about 5G, every generation it improves all the key performance indicators by tenfold. So likewise, so 5G support massive Internet of Things. I'm sure you are familiar with the word of Internet of Things, because in the past we talked about users, but in 5G we talk about things. So things entitled to people, to societies, organizations, systems, and all sort of machines. So it's not only about users. So we talk about the things. So it supports massive Internet of Things, and with our key performance like deep converge and ultra low energy, because that's why I use the keyword of green communication, and then ultra high density, because we are expected to have really high, large number of small cells to connect these all billions of devices, and that end up by having ultra high density networks in the world. So then, other one I think I already explained this, so let me go to the next slide. So this slide I really like. It talks about what is really 5G. So 5G comes with some key technologies. One of them is millimeter wave. Millimeter wave is generally we have been using up to 2.5 GB, and then now with 5G we could use unlicensed band, and we can access up to 6 GHz band, and that was never been accessed in the past. And when we were students, we were told it is not possible because we can't develop such antennas. And probably from your physics, you know that wavelength is inversely proportional to the frequency, right? When the frequency goes up, wavelength needs to go down. And then that is also parameter of designing antennas. But our antenna research groups has came up with millimeter wave antennas. So it is now possible. So the millimeter wave will support to solve our spectrum problem. And secondly, non-orthogonal multiple access, or NOMA, that will support large number of connected devices. Just to get it understandable, probably you know OFDM. Do you know OFDM? Have you heard? OFDM, orthogonal frequency division multiple access with 3G, no? Probably you heard CDMA 2000, right? So these all technologies we call multiple access technologies that support to connect number of devices. in OFDM what we do, it is like a highway, right? It's like a highway strips, and each user is given a one frequency strip. And that's why we orthogonally divide in the users, right? But as I mentioned, since the frequency is very sparse, we cannot keep allocating frequencies spectrum for each user. We need to find new way of thinking. So I was at a European project meeting in 2016 where we discussed about what would be the new multiple access technique. Because in 3G people talk about OFDM, and 4G people talk about OFDM-A with the it married with the time division multiple access, and the idea came out with Professor Jayakody from Manchester University, the NOMA, not orthogonal multiple access. What we do is, in multiple NOMA, we allocate different power content to each user, and thereby the receivers can detect that power power level, and identify that particular user. So we put 5 people in a one frequency strip and ask them to run, But the destination, the receiver can identify them by looking at their power content. So this is what we do in NOMA in simple words, right? So that support large number of devices that also help to achieve our target of ultra low latency. And then massive MIMO. Massive MIMO is we have a large number of antennas placed together. MIMO is multiple input, multiple output. This is another groundbreaking technology that comes after LTE-A. So that can actually improve the degree of freedom, because if any antenna element got failed, others can support, so others can keep the communication. But in the past, with a single antenna, so if one antenna is break, you are gone, right? But then the MIMO came, and now with the massive MIMO, there will be 200 antennas placed at one place. So that provides very high capacity. Okay, so I just have to, okay, this is 5G plan of the world. So let me just go to this slide. So 5G is, in 5G we look at quality of experience and not the quality of service as it was the case in the previous generations. So we want to see, not from the network perspective, from your user perspective. How do you feel our technology? And socially, to what degree is acceptable, right? So we measure all these qualities, and then we see that the technology is user-friendly or not. So in the past, when we deploy any technology, we always look at technical point of view only. So that is why the quality of service was in the news and everywhere you heard. Now you will hear quality of experience. So we want to keep the user as the central focus of attention. And then 5G talks about things, not users, and then when will 5G come out? Still 5G at the research phase, and some companies implemented the commercial version. So why isn't rolling out faster? It's because of number of reasons. One is infrastructure cost, and secondly, still the research is going on, but we expect 2020 many of developed countries will have some experience, and China is going to launch it next year. So when will 6G come out? Oh, come on, we haven't even heard of 5G, but still, people already started research on 6G. I'm sorry I have to wind up. I haven't presented our research results, but I'm happy to answer if you have any questions.
If you have any more slides, you can just
Okay, sure.
before the slide.
Yes. So I will show some of our research results. So this is about energy harvesting. Have you heard the wireless energy transfer? Yeah, that means, in a common term, you can charge your mobile phone while you are having your chat in a coffee shop. So if you just keep your mobile, you will get charging. So we use same electrical signal that comes to the mobile phone for harvesting energy. So the portion of signal will be used for information decoding and another portion for energy harvesting. So we have implemented this in the drones communication. This is one of my research interests. So we improved the energy harvesting efficiency by 39%. And here we actually use some time division optimization technique. where we optimize the time allocation. And the interesting thing is we use interference. And probably you know in wireless communication, interference is the enemy. But we use interference as a useful resource to harvest energy. So interference is no longer an enemy for wireless communication. We use for harvesting energy. So in this scenario, we have used a drone which is used in an urban scenario and then connect with two distance users. And the drone is fully harvested by RF energy. And then we improve the energy harvesting efficiency by 39.23% relative energy harvesting efficiency. So I'm not going into much details. And then we use drones as an antenna here. Now you know drone is used for capturing images or cinematography, but drone can also be used as a base station. We call it aerial base station. So we came up with the idea, aerial base station idea, a drone that can use for on-demand service. Let us say that this gathering and everybody wants to use mobile phones. So there may be thousands of people gathered at KTU today. But the network operator is never been informed, right? And suddenly people are going overloaded with the messages and they cannot access the mobile phone. So the network provider can send the drones here and then operate them as aerial base stations. So they can dynamically set up a cell without you knowing it. So the drones will be standing on the buildings and providing the coverage. So that's a simple understanding. And our paper was accepted by one of the prestigious journals, IEEE communication magazines. And our previous work was accepted by the IEEE transaction of vehicular technology. So if you have any questions, I'm
Right. The question I asked, I think you answered partly in the last question.
Okay.
Now, UAP is green 5G. So that means we are not going to have structures.
No, this is a dynamic structure because it works on-demand basis, like not like stationary base station. So if there is an on-demand, like for example, if there is a flood or earthquake, when the whole communication structure is damaged, we can use UAV as a base station using our proposed method. We also use machine learning technique to detect where the large number of demand is, and then the drone goes there and stand on that position.
Why do you call it green?
So we call it green because our communication or the modules embedded in the drone is fully used by energy harvesting.
We have about 5 minutes more for questions.
Could you please comment about the health and safety issues of IEEE technology?
Alright, thank you very much for your question. And I was on the European project meeting in Poland last week, and at given any point, nobody discussed about this. What are the health effects? Actually, unfortunately, in my understanding, there is no proper research is done. But when it comes to the millimeter wave can travel only 1 kilometer distance. And the problem is it can be absorbed by any physical object. So that means if humans are in the vicinity, that can be absorbed by the human body, which will improve the heat of cells. So that can be hazardous. Like it may cause, if I'm not mistaken, ionization of your cells. Yeah. So that is something that I know in my mind, but it's always, even when the GSM was implemented, there was a lot of strikes in different countries. But we always come up with a way to tackle it. But I also agree with you, we should have more research on health effects of 5G.
Professor, Professor, yeah, I do have a question. Now, when you talk about the drone, now you said that it harness RF radio frequencies, right? So that means, is it part of the radio frequencies used used for energy harvesting and part for signal control. Is it that what you mentioned? Because that isn't that loss of information?
Yeah, I mean, you asked the right question. So let me just go back to our slide. Here. So here we use three sources of information in energy harvesting sources. First one is the dedicated wireless power transfer that will have very high need to harvest the initial need of the battery. And then once the communication started, what we use SWI, simultaneous information and power transfer. And using our optimization technique, we guarantee the minimal requirement of the data rate. So it will definitely affect the data rate, but using the optimization techniques, we can minimize the loss. So the quality of service will be guaranteed, though there will be a loss of information, but there are other techniques actually, we call it shaping. Shaping means, so if you look at the simple constellation diagram, what we do is, we maximize the energy, high energy bearing symbols, right? And then the information were only kept at the low energy bearing symbols. So thereby we don't cost to the data rate.
So that means the line of sight should be there?
No, line of sight doesn't really.
It doesn't. Thank you.
It's just that we realize the line of sight due to the drone here.
Thank you.
We can have one last question.
My question relates to the previous question on the electric wavelength. If I'm not mistaken, the same wavelength is used for radar control, fire control radars.
Yeah.
So it is being used. It is
used, but not in a very public, in a massive way. Because with the 5G, we can use it for commercial deployments. I mean, people kind of knew about it, but they never used for a mobile communication system because they didn't know how to build commercial antennas. All right, thank you very much.
Thank you for that. The next topic is unlock space access for manufacturing. Reaction engine and the further propulsion system by rear admiral Humankind. Humankind served as an aircraft engineer officer in Royal Navy for 32 years. After normal provision for operational and support roles, he served as a UK lead in the US-UK Joint Strike Fighter Program and subsequently led the UK Joint Combat Aircraft Integrated Project team for 4 years. His last job before retirement from the Royal Navy was as technical director and head of program management for defense equipment and support organization. He laid the foundation for the current professional career structure for program managers in the Ministry of Defense. He subsequently joined Rolls-Royce as a program director for new programs in defense and aerospace. In 2010, he was seconded to Europe International as president, responsible for the development, verification, and introduction service of the TV400 engine and for the A400 aircraft, culminating in the delivery of the first aircraft to the French Air Force in 2013. He is currently working for Reaction Engines Limited as business and industry strategy advisor, helping them to bring the revolutionary Sabre engine to market to revolutionize access to space. He was the elected president of the Royal Aeronautical Society for 2018-19. He's a fellow of that society, an honorary fellow of the Association for Project Management, and a fellow of the Aeronautical Society of Moratuwa. Over to you.
Thank you very much indeed. This is going to be quite fast-paced, probably appropriate for an ultra-fast engine, a hypersonic engine, but it's going to be a hypersonic presentation. This is quite compressed. So let's where are we now? Man has been going to space, or man has been sending things into space for 60 years now. And over there you can see from some of the very early rockets right through to some of the things in the 70s, right up to the latest rockets from the space shuttle. Some amazing things have been achieved in that 60 years. Tangible benefits to our everyday life. We all drive around, probably, certainly in the UK, we all drive around absolutely depending on having GPS in your car. Nobody uses maps anymore to get around. Ships are able to navigate around icebergs because of global observation coming from space. And the whole of the interconnection of the world, the middle slide there showing the 2012 Olympics in the UK, transmitted worldwide because of satellite communication. In parallel, we've expanded our understanding of space. We know an awful lot more about what's going on in space. We have a lot more observation out there. So we've made huge steps forward in space and what it's achieved for us. But while those space things have moved forward, the actual vehicle we use to get into space has actually not changed very much. It's carried us a long way so far, but we've still got some inherent characteristics in today's rockets which we could really do without if we're to make the next step to space access. They're very expensive, primarily driven by the fact that most of what you actually launch from the rocket pad you can't reuse. It either goes into space as space debris, or it comes down and goes into the ocean and you scrap it. At best you can recycle materials. They're difficult to operate. Vertical launch rockets are only stressed to actually be loaded in a vertical direction. So in order to stage a vertical launch rocket with its payload, you have to build it on the launch platform and then put the payload on the top. You can't load it off-site and then lift it up into position because the stresses can't cope with that. And vertical launch rockets are inherently unreliable. The current failure rate of vertical launch rockets, even in today's age, is 2%. That means if Elon Musk wants to put 1 million people into space using vertical launch rockets, he's going to kill 20,000 of them. That's probably not a very acceptable statistic for air transport. So all of that increases the cost of space and restricts growth of the space market because it's so expensive to put things into space. There's been very little change in launch technology in over 60 years. So on the left-hand side there was the first rocket that was launched in 1957, right up to the Soyuz aircraft, the Ariane, and the big aircraft, the big rockets of today. Very little has changed in terms of the fundamental technology. If you look across the last 60 years in aviation, things have changed markedly. In 60 years, I'm going to take a timeline from the first flight in 1903 through to the late 60s when Concorde flew. You'll see that progressively the air vehicle itself changed markedly. The way it operated changed. We went from very low speed, very low range flights right up to supersonic flights across the Atlantic with Concorde. And the things that drove that change were primarily breakthroughs in propulsion technology. The first aircraft was only enabled when somebody could actually get an engine that had enough power density that it didn't outweigh its ability to provide an aircraft with lift. Over time, the engines developed in more reliability till we got to something like the DC-3, which was getting close to the ultimate development of piston engines. We then moved into the jet era with the Comet, and then into the afterburner supersonic engine with Concorde. All of those breakthroughs were led by propulsion technology. The other piece that's made aircraft so usable is the fact that the only thing we have to take with them that gets used is fuel. The air that they use to actually do the combustion in the engine comes from around them, and therefore you don't have to carry it with you. So unlike a rocket where you carry your oxygen with you in a tank and your fuel, on an aircraft you just have to carry the fuel. You take the oxygen from the air around you. And the other lesson is that use of runways rather than vertical launch is the simplest and most cost-effective way to actually get into the air. So taking off from runways, coming back to runways is the safest and least damaging way of operating. The other piece is that if you design your machinery for reuse, then the high rate of use leads to, allows you to continually improve as you learn from the experience, and you can reuse items so that it brings the cost down. The same is true in the military world. Same sort of advances from left to right, from the Wright Flyer right through to a modern Generation 5 aircraft like Typhoon. The same things apply. Breakthroughs in propulsion technology, the fact that you don't have to carry anything other than your fuel with you, horizontal operations, runway. There are obviously military aircraft that don't use runways, that go off vertically, or more importantly, land vertically. But that actually gives you a limitation on the aircraft. The most unconstrained aircraft are those that take off and land horizontally. So let's bring that model to space launch. We just have here the 3 degrees of freedom of performance, affordability, and operability, and let's say that that's the current propulsion size. So as we started that 60 years of rocket development, early launchers very rapidly pushed the rocket performance boundaries, so they went up the vertical, up performance, but at the cost of affordability and operability. Nothing changed there. There are new people now out there, Musk, SpaceX, and the Blue Origin, who are trying to change some of those paradigms. They're trying to improve cost and operability by introducing elements of reuse, elements of recycling of the elements, but the achievable gains all the time you stay in vertical launch rockets with current technology are only moderate. If we're going to really revolutionise access to space, then we require new architectures and new possibilities which bring a drastic increase in launch system propulsion performance. And if you just run on the propulsion system, just as an expansion of the current one, that will not give you that expansion you need. We need to look at something completely different. And that something completely different is the Sabre engine. Synergistic, air-breathing rocket engine. And basically what we do is, this is a rocket engine that thinks it's a jet. So basically, looking from left to right there, as it's going through the atmosphere, it's breathing air. It's not using onboard oxygen, it's taking the oxygen in from the air around it. It's then cooling it down, and I'll talk about that in a minute, because when the air is coming in at the speeds required to get out of the atmosphere, Mach 5+, the air compresses and gets extremely hot, too hot to put through an engine, so you need to be able to cool it. It then compresses that air, once it's cooled it, and passes it back to the rocket nozzle at the back, where it's then combined with liquid hydrogen fuel and works in a pure rocket mode. There is actually a bypass duct that you can see there. There are bypass burners there that give you extra thrust while you're going through the atmosphere, and that's just about the fuel efficiency. So how does that work? So this is the engine, airflow going left to right. So first of all, the air is coming in at Mach 5. Anybody that's done any aerodynamic theory will know that you can't use supersonic air. You have to slow it down to subsonic to feed it through the engine to get rid of compressibility effects. As soon as you slow it down, and that's what happens on the left-hand side there in that intake, the air heats up and it gets up to 1,000 degrees C, which is enough to melt your engine if you try and put it through. So what you have to do is actually cool it. And the first, I always say there are 3 miracles required to make Sabre work. And the first miracle is you need to be able to cool that air from 1,000 degrees C to roughly 0 in a 20th of a second at the rate required to feed a rocket engine. And that technology is now proven and working today. Once you've done that, you actually put the air through a compressor which works very similarly to a gas turbine. So it's a compressor driven by a turbine. But instead of using any fuel to actually drive the turbine, what you do is you extract the heat that you've taken out of the intake at the front there, when you've gone through the cooler, you transfer that heat into helium, and you use helium across the turbine to expand the helium and take the heat out of it again, and use that work to drive your compressor. Ultimately, the helium will come out, it'll still be slightly warm, so we then use another heat exchanger cycle with the liquid hydrogen that's on its way to fuel the rocket to cool the helium right the way back down, and then the helium is fed back in its very cold state to do the next round of cooling. So the helium is effectively in a closed cycle, and what we're using as fuel is just the hydrogen, take the residual heat from the helium, and then burn it in the rocket nozzle. So what does that give you? Well, what it gives you is an engine that works across the whole Mach range from 0 right through to Mach 5 plus in the atmosphere and Mach 25 if you go into space. And it's incredibly efficient because if you try and do this in any other way, then a number of engine concepts that are shown there will cover part of that envelope, but none of them are efficient across the whole piece. So on those two graphs, the left-hand one is effectively a measure of efficiency, which is specific impulse. And that shows you that at slow speeds, then a turbofan engine is the most efficient there is. But we are within the range, even at 0 speed, of the efficiency of a turbofan. But as you get faster and faster with a turbofan, the efficiency drops right off. The Sabre engine holds on to that efficiency right the way up till it goes into pure rocket mode when you get out of the atmosphere. And basically what happens then is the intake closes off, and now the remainder of the time in space is actually worked on as a rocket would, with stored oxygen and stored hydrogen. At that point then the efficiency comes down to that of a normal rocket. The right-hand side is a measure of thrust and weight effectively, and shows that again this engine is way above any other form of engine or even any other combination of engines in thrust and weight until it gets to a combination with a comparison with a direct rocket. So the great things are, it operates from a standing start. So now you can actually use this in a horizontally launched aircraft that goes off the runway. You get extremely high fuel efficiency in air breathing mode up to Mach 5.5, better than any other engine that's out there. And then once you get to the top of the atmosphere, it switches to rocket mode in order to, because there's no longer any atmospheric air around, and now you're using onboard oxygen. And at that point, you're then working the same as a rocket mode, and your efficiency and your thrust weight are the same as a rocket. So what does that allow? What it allows are a completely 100% reusable space plane. Space operation has now become like an airline operation. If you're going to take an aircraft off horizontally, you could just put the payload in the back, you take off from a runway, you climb to height, you send off your second stage into the exo-atmosphere, and then you return and land again. And then you can use the same aeroplane to do the same thing the next day and the next day. The engine is lifed to 200 cycles, and therefore we can actually use it 200 times around. There will be some maintenance required between, but it is now much more like operating an airline. And that gives you low cost, an order of magnitude lower cost, so at least a tenth the cost of SpaceX and where Blue Origin are today. Very high operability, which means that the horizontal takeoff means you can handle it just like another aeroplane, and very high reliability, because if you've got two of these engines on, at the moment if you have a rocket that's on vertical launch, when you press the go button, everything that's on that rocket is either going into space or it's going into the sea. If it fails, it's going in the sea. What we have is the ability, because this is taken off horizontally, should you get a single engine failure, the aircraft will be able to recover, and therefore you get much greater safety. Just speeding up here. So there's the typical cycle. Aircraft takes off from a horizontal runway up into space, air breathing until it gets to the top of the atmosphere, and then into rocket mode at Mach 5, and then places the satellite in circular orbit and recovers. So what does that actually do for us? Well, it gives us on-demand deployment of space-based assets. For the military, you've seen the announcement very recently that Donald Trump is militarizing space. Militarization of space has already happened. Shooting satellites down has become a weapon of war. Therefore, if you have military satellites that need very quick replacement, you can have one of these vehicles on call, and should you lose a satellite, you can redeploy and get another satellite up there within hours or days. It gives you that rapid constitution of satellite networks. It can do launch from multiple launch sites. But also, it can revolutionise space access for mankind. That reduction in cost enables a whole lot of other things that are good for mankind. So let's ignore the military side. One of the things that is possible in space is space-based solar power. In order to get space-based solar power, that is free energy from the sun with zero environmental effects. However, to make it happen, you need to get about 8,000 tons of satellites into space in order to pick up the sunlight. That is completely unaffordable today, but with this sort of system, it would revolutionise it. Is it real? Bits of it are. So this here is the heat exchanger that actually does that cooling. So we have that running literally today in a test site in America, and we are proving that we can cool the air from 1,000 degrees C, Mach 5 equivalent, down to 0 at the rate required to feed a rocket. That technology is real. It's existed now for about 3 or 4 years. The BBC were publishing it about early this year, and it's happening. That's the test site in America, top left, that we're doing it on, and that's the technology we're doing it with. The plan for reaction engines is, we have UK government funding at the moment. We will expect to test the rest of the engine at a breadboard level next year. So the technology for this engine will be real next year. We are aiming for a rocket platform that will be the next generation, probably the next generation European space program for 2030. And that's what that looks like. In the meantime, we do expect to be able to do a demonstration of the engine in flight in 2025. That probably, if you look at the technology, cooling that air, you don't necessarily have to have a full Sabre engine and a rocket engine behind that cooler. You can actually do it with a gas turbine. And it actually gives you about 1 to 1.5 extra Mach on the gas turbine. And that's what we will intend to fly in 2025, is a demonstrator of the cooler in front of the gas turbine. And then we move on in the 2030 timeline to space access using a full-up Sabre engine. So I'm very, very privileged. I've had an incredible career in engineering, and this is, I think, my last job. I keep trying to retire and don't do very well at it. If this is my last job, then believe me, I couldn't be happier. It is the most exciting place to work I've been in for a very, very long time. Thank you very much. I'm happy to take any questions. Somebody must have a question about space. Glory.
How long do you need the first horizontal propelled?
How long the runway?
No. When do you think it will actually take the same years to space and we come back?
Oh, I see. Well, the typical burn of the rocket engine to get from the runway into space is about 6 minutes. So you'd be out of the atmosphere in about 6 minutes. Probably another 20-30 minutes to get to the point where you would then release the second stage, and then back in less than an hour. You did a re-entry and then the descent. So a mission cycle is probably about 2 to 2.5 hours.
Admiral, I got a question. Now, how is this different from shuttle carriers?
Okay, the shuttle, if you think about it, was launched vertically. So
no, shuttle carriers. Shuttle carriers like 1747. I just looked into the internet. Like in NASA, they are using shuttle carriers. Like they launched the space shuttle on top of a Boeing 747 to make sure it orbits.
No, the shuttle launch was always vertical. So they were strapped vertically to a rocket, and if you think, it also had 2 huge oxygen tanks with it, because the rocket that it used was not air breathing, so it went off in vertical mode. And as we saw, that when they had the problem with the shuttle, when the tile came off, then that's very vulnerable to failure. There's no recovery from that. So the 2 differences are that the recovery is very similar. So as the shuttle used to come back down and come onto a runway and then could be recycled, that is very similar to Sabre. But the bit that's very different is the fact that we don't use tank oxygen to get out, and we've got a recovery mode should you get a failure on takeoff, so you can actually recover and land on failure.
So, if you use this engine, like the one which you suggested, now if I'm not mistaken, shuttles can be reused twice or thrice?
Yes, it is. Yeah. So the engine is scalable. What we would do is actually you scale it by putting more and more modules together. So
okay. So how many like cycles can be used if you use this particular engine?
oh, so per engine is 200 uses per engine.
Wonderful. Thank you.
What could be other applications of that energy using technology?
Sorry, say again, my hearing's not really.
What could be other applications of that energy reusing technology?
Okay. So there are a number of the engine itself. The Sabre engine is certainly usable for space access, and some sort of hybrid between Sabre and a gas turbine with the cooler on will almost certainly be what powers the next generation supersonic or exo-atmospheric aircraft. So we hear tales of 4 hours from London to Sydney, that's one of Boeing's intentions. That would be, the engine for that could well be something that's akin to this, a pre-cooled engine with either Sabre rocket technology if it's going to go exo-atmospheric, or if it's going to stay in the atmosphere, it would probably have a gas turbine behind the pre-cooler. But if you break it down, there are technologies that have contributed to that. The cooler technology that we have developed is completely unique and game-changing. And we thought it was good, so we thought, well, who else can we talk to find out if it's as good as we think it is? So literally a year ago, we started talking to, and to be careful what I say, I would call it the very high end of motorsport, as in the top league of motorsport. And as a result, next season, there will be 3 teams at the very high end of motorsport that will have radiators that are designed and made by reaction engines using the same technology as we've got for our pre-cooler. Because we have shown that our coolers are at least twice as good as the very best in the world using current technology. And that cooler technology now we're looking at very hard as to where that branches out. There's all sorts of things that are coming out of our understanding of how we transfer heat, which is what this engine is all about, moving thermal energy around, and how we can actually, what the technology can be used to actually make that transfer. The cooler that I showed you on the slide is about that big in diameter, about that long. And it's an angular, so it reads from the outside to the in. There's 47 kilometres of thin wall tube in that cooler, which gives you the heat exchange area that allows you to get that very rapid cooling.
Thank you.
This will be the last section.
So good afternoon, sir. I'm Jayakody from SU Fernando. I'm an undergraduate in Aeronautical Engineering in KDU. Sir, may I know what's the purpose of having unconventional types and plant services in the hypersonic aircraft? What's the purpose of having?
Sorry, yeah, okay, got you. I think I've got it up. I'm sorry, I spent 2 years on board aircraft carriers with Harriers, therefore my hearing is not that good. So I do apologise. So hypersonic aircraft, yes, we are now working in defence to look at hypersonic aircraft. So it was announced about 2 months ago. We've got our first contract from the UK Ministry of Defence, and that will see us actually putting our cooler on the front of the engine from a Typhoon, an EJ200 engine out of a Typhoon fighter. The first stage is just to prove that the benefits that we think we'll get from cooling do actually work, and actually make sure that you can integrate the cooler straight onto the front of the gas turbine engine without difficult mechanical interactions or airflow. We've run it in front of a jet engine before, so we're pretty confident that this will actually be a fully instrumented engine so that we can see where we go. From there, we will look at how we can then apply that to get into a hypersonic demonstrator, which, as I say, we hope to fly in 2025. So that would be very much just a test aeroplane. It might be small scale, but it will prove something that has defied the US to date. The US has spent many billions of dollars on trying to get an aircraft that goes from zero to hypersonic. What they basically have is a dual cycle engine. It starts off with a gas turbine, and then as it gets up to the hypersonic range, it switches from gas turbine, because the gas turbine's got all the limitations of the air is too hot. It switches from that to a ramjet or a scramjet. The problem is that it's really, really hard to get a gas turbine fast enough that your ramjet or scramjet will light reliably. The ramjet wants to be going faster than the gas turbine will push you. So there's what we call the valley of death in between, where you can't get fast enough on the gas turbine to get a good ramjet light, and therefore it's really difficult to do. By pre-cooling the gas turbine, you can actually push yourself right through that boundary, and you can close that gap, so you can get to the point where two things happen. Firstly, you can now go on to reliable ramjet or scramjet propulsion. The second thing is, unlike on the combined cycle engine, you don't need to shut the gas turbine down, because you're still pre-cooling. You won't be running it at full thrust, but you can actually have it in flight idle condition. Because you're cooling, the engine can survive those conditions, which now means you can use that for generating power. So now, instead of being a hypersonics being just a missile that relies on battery and stored power, you've now got a source of electrical power, and you can use it for information, surveillance, reconnaissance, whatever else you want to do. Or if it's on a civilian liner, then you're producing power for the passengers and the accommodation. So it offers massive advantages, and is a great step forward in the hypersonics. And it's no accident that, amongst other people who've invested in reaction engines, we're only 200 people in our company, but we're invested in by Rolls-Royce, by Boeing, by BAE Systems, and we certainly, in the year that I've been there, virtually every major aerospace company has walked through the doors and taken a good look at what we're doing. It's a really interesting piece of technology.
Thank you. Thank you very much.
The third presentation for the session is design and fabrication of smart piezoelectric devices. The speaker is Professor Shiromal Adikary, who is a professor of Material Science and Engineering of the University of Moratuwa. Professor Adikary has been working as an academic staff member of the Faculty of Engineering for more than 25 years in various capacities. He is a chartered engineer and a corporate member of the Institute of Engineers, Sri Lanka. Professor Adikary has been head of Department of Material Science and Engineering for 9 years, and has been the director of the Staff Development Center at the University of Moratuwa from October 2016 to March 2019. Professor Adikary possesses an excellent record of accomplishments as a university academic and a professional engineer. He has authored more than 70 peer-reviewed research publications in index journals and international conferences. Researchers all over the world have cited his publications more than 400 times. He is a recipient of 2 presidential awards for research excellence and 3 awards of excellence in outstanding research performance at the University of Moratuwa. He has been a consultant to the installation of the multipurpose irradiation plant, Chairman of NSF, National Committee on Advanced Materials, Co-Chairman of the National Council on Advanced Materials of Custody, and member of the Advisory Committee on EDP. Over to you.
Good afternoon, ladies and gentlemen. Sorry about the technical the title of my presentation is Design and Application of Smart Devices. And the contents are given here. First of all, I will do a brief introduction to smart structures. And of course, smart structures contain basically sensors, actuators, and control systems. So, in this presentation, the research that I present are basically centered on these related sensors and actuators. So, therefore, as number 2, I will do a brief introduction to electricity and piezoelectric materials. Then piezoelectric vibration energy transfer devices, piezoelectric vibration sensors, and some details about the two research projects that we have carried out at Moratuwa. First one is design and application of vibration energy transfer device, and the second one is the vibration sensor related to video vibrations. Both projects are basically similar in nature, that involves mathematical modeling, finite element analysis, and development of prototype and testing of prototypes. First, smart structures. Of course, my previous presenters also mentioned smart things, basically smart vehicles, smart business, so everything is smart nowadays. Now, in the case of smart structure, the system that incorporates functions of sensing and actuation to perform smart actions. Basically, a smart structure mimics a biological body by performing many desirable functions, such as synchronization, environmental changes, self-repair, etc. To consider a smart structure basically consists by components. So it must have the data acquisition ability, that is a sensor, and the data transmission, command and control, it should have a control unit, data instruction, and the action devices or actuators. So then how these materials, smart materials, become a part of smart structure? So as I mentioned, basically you have three components: sensor, actuator, control system, and of course data transmission and data instructions. But especially sensors and actuators You have smart materials or functional materials. Sensor is basically sense a change in the environment. If there is stimuli, change by sensors. Many sensors are built on different types of functional materials. Then of course sensor signals goes to the control unit, and then it forms the analyze the data and instruct to actuate the actuation action. Again, actuators are also solid state actuators, basically based on the materials. So I have two examples of smart structures. One is smart piezo shock absorber, and the other one is schematic diagram of smart bridge. So in the case of a smart piezo shock absorber, also you can see piezo sensors are there and the piezo actuators are there. So when a vehicle goes through a hard terrain, for example, it can detect, the pilot sensor can detect the road condition by sensing the vibration, and then actuators do actuating action to mitigate the vibration. So that is a smart device. And also similarly in bridges, etc., you have a lot of sensor networks basically using fiber optic sensors, and sometimes you may have piezoelectric sensors also. So sensor collect different data debrief and then send to control unit or process the data and say to take remedial actions based on the severity of the damage or cracks or whatever. As I mentioned earlier, sensors and actuators are mainly based on functional materials. So we have to kind of identify what are the requirements of sensor and what are the requirements of actuator. So sensing components of smart structure are designed according to the nature of the event to be sensed, nature of the output required at type of environmental conditions. And I have some examples here. In most of the structures, smart structures, depending on the stimuli, people use fiber optic sensors, shape memory alloy sensors, piezoelectric sensors, etc. And similarly, actuators, these are action devices. On instruction, it can deform or create strain as actuation actions. Again, you have smart materials or functional materials like shape memory alloys, nanoconstrictive materials, and piezoelectric materials. So how smart structures or how smart materials contribute to smart structures are given in this chart. You can see the smart materials and smart materials used in industry, piezo materials, nanoconstrictive, multiferroid, ferroid type materials, ferromagnetic, nanoconstrictive materials, combined smart devices like sensors, transducers, actuators, motors, with the support of other infrastructure like signal processing, control units, energy harvesting, etc., can build up a smart system or smart structures. So in our research, basically, the material, the smart material that we use is piezoelectric material. So a little bit about piezoelectricity. Piezoelectricity is defined as the electric polarization produced by mechanical straining. Crystals belong to certain classes. The polarization being proportional to strain and change in sign with it. So that is basically the direct piezoelectric effect. So if you have a piezoelectric material, then if you stress the piezoelectric material by applying a force or load, then it can generate an electrical signal, a voltage, or sometimes electric field. You have a converse effect also. That is, if you apply a voltage difference or electric field to a piezoelectric material, then it can create a strain or deformation. So the direct effect is basically something like a sensor, and the indirect effect is something like an actuator. So this diagram is clearly illustrated. You can see the converse piezoelectric effect. We apply voltage difference. You can see there's a strain generated. If you change the polarity, you have the opposite direction, the deformation. In the case of first one, you have the tensile load is created. The other one, of course, the compressive load is created. So that is similar for the direct piezoelectric also. If you apply a force, you create a voltage, DC voltage, and if you apply a force in the opposite direction, the sign is changed. So therefore, basically, in piezoelectric effect is an anisotropic effect. It's an anisotropic effect, and basically the directions are dependent on the crystallographic planes. The piezoelectric effect can be calculated using the constitutive equations, which are in matrix forms. So for the converse effect, you have the equations, and for the direct effect also you have the equations. If you consider the materials, piezoelectric materials can be categorized basically in three categories as natural crystals, man-made ceramics, polymers, and lead-free ceramics. So out of these three, the man-made ceramics, which are synthetic ceramics, are capable of providing the piezoelectric coefficients that are necessary, that are required for industrial and commercial level applications, especially materials like lead titanate, barium titanate, and lead zirconate titanate are heavily used in the industry. The fabrication of piezoelectric ceramics is not very complicated, it's very simple method. Of course, even in our labs we do these fabrications. This is basically powder-based technology. We have to have low stages in powder form. Then of course you do mixing the process. Of course during mixing you have to think about stoichiometry also. And then you go on this ceramic processing, finally you do the sintering, and after that you have to electrode the samples, and then you have polling operation. Polling operation is very important. If you don't do polling, piezoelectric material is not active. So to activate, you have to do the polling. Polling means you apply very high DC field to activate the domains of piezoelectric materials. And after that, of course, you can use it in different applications. So piezoelectric sensors are there. In the piezoelectric sensor function is similar to direct piezoelectric effect. If you apply a FRAeS, it generates a voltage. So therefore, basically now, for example, guitar pickup is a piezoelectric sensor. It can pick up the vibration and generate a current. Similarly, you have piezoelectric actuators, different modes. Now the diagram shows two multi-layer type piezoelectric actuators supply the DC current so that you get a strain. So the applications of piezoelectric actuators are in the industry, like piezoelectric motors, atomic force microscope, MEMS, fuel injectors in diesel engine, etc. So I skip this. And very brief details about piezoelectric vibration energy harvesting devices. What is the importance of these devices, especially in electronics, electronic garments, portable electronics, wireless sensor networks, especially in the MEMS. If you consider these three types of devices, the power requirement is comparatively low, and if you do batteries, of course, you have less enough for carrying the battery, etc., replacing the battery. Especially in the wearables, of course, people wear the device so that you have enough vibrations, etc., to generate the energy. So once you generate, you can harvest by a piezoelectric sensor and use it in the device. So energy harvesting is based on the external energy. You should have some external energy, basically mechanical based external energy, and then can convert the energy using the piezoelectric sensors, and you have to have a captor circuit for that, and then you can supply to the load circuit, or you can you can charge a battery, etc. In the case of piezoelectric vibration sensors, the principle is again same. We use the direct piezoelectric effect. So you should need a vibration object. Then we have to build a mechanical structure to extract the vibration. And then from that of course we get a signal. Then of course you have to analyze using some mathematical, complex mathematical techniques to get this signal. Okay, the project one is design and application of vibration energy harvesting device. Objective was to use vehicles, especially vehicles mean vehicles like three-wheelers and motorbikes, where you don't have vibration, good vibration damping system, so that you have some vibration to generate electricity. The methodology that we use is first we identify the sensor configuration, then analyze the vibration source, so there is some frequency. Then we do mathematical modeling to design the prototype. Then we simulate the dimensions of the cantilever, the model, and we prototype of piezoelectric device. So we use cantilever model as the configuration, and then of course to design the sensor we should know the resonance frequency of the range that we are going to analyze. For that of course we did some tests to analyze the target vehicles, basically using accelerometer, and you can see for different type of vehicles like motorbikes, bicycles, and three-wheelers, we analyze the amplitude with frequency data, and from that of course we decide to have a resonance at around 35 Hz, and then with the mathematical modeling. So this at least. Sorry? Alright, sure. So finally we did the prototype, and suppose the prototype results and model results compatible, and we did the publication. And similarly we did the application of vibration sensor, same model, but the analysis was different. So this is the prototype. To get the vibration sensor, you have to get the frequency and the amplitude. To analyze the vibration data was difficult. We use fast Fourier transformation, and from that of course we get the voltage generated and the amplitude and frequency. We also publish results. The acknowledgements, the funding for the research was provided by Shiromal Lanka, and also I'd like to thank my research students, Ms. Janata, Ms. Nasara, Mr. Yusilva, and Anand. And thank you very much for your attention. Thank you.
When you connect these piezoelectric devices to a wall or something else, will the characteristics of those change?
No, it will not change.
How important is the method of connecting the device if you want to make measurements?
The vibration should be able to transfer to the device, and the device should stably, adhere to the structure.
Thank you very much for the interesting presentation. Can we go to your slide number 3, heading into number 3?
Number 3.
Yeah, there was a heading in 3 points. Yeah, no, yeah, not this slide down on the title, 3 points.
No.
Yeah, here. So when we get this external energy to harvest, and when you do the energy conversion, there is a loss of energy. So what is the percentage of energy conversion? And also when you store them in the battery, and also there will be another another loss will be added. So my first question is, what are the energy losses or the efficiencies? And then, is there any smart ways of minimizing it?
In the case of vibration energy, of course now the model that we use is a cantilever model. The vibration transfer from the mechanical system to the sensor happens through the cantilever. So the transfer should be maximum, but that depends on the design. In the case of first project, we randomly selected the target vibration and then assume a resonance frequency. So if it is resonance at that, then you get a maximum vibration of cantilever, so that you get a maximum extract. But in the real case, that is not the case. So you have a loss there. And also in the piezoelectrics, depending on the material parameters, you have a loss. And if you have other things like heating, again, you have a loss. So exact percentage of course in literatures people say anything, but for us, I think we are not doing that.
Maybe one more question on the vibration energy. So the vibration energy can be used in the airplane as well, because when you travel, you see there's this huge amount of vibration. So can it be used for energy harvesting?
Yeah, but in the air travel, maybe the temperature is outside temperature is very low. So at that temperature, piezoelectricity, I think is not very active. Because piezoelectric depends on the this kind of phase of the material. Phase changes occur depending on the temperatures. Now the PECT is basically maximized from room temperature up to about 200 degrees like. So if you go below, then you may have an issue because it may transform to a low symmetry phase. Then of course, then of course it's not electric. Only several phases has this piezoelectric effect. Especially phases that doesn't have sense of symmetry.
Professor, now how long, now if you install a piezoelectric device for energy harvesting, how long does it take to replace again?
Yes, there's a fatigue effect. There's a fatigue effect when you use for a long time. But for this research, what we have done was, we bought the piezoelectric materials from a US company. It's called APC, London Piezoelectric Corporation. So when we give the specifications, they do the sample and they give the fatigue number of cycles. So that is the lifetime.
So it means a continuous operation?
Continuous piezoelectric.
So if you can...
It's very easy because in the cantilever you have a place, place where you put the piezoelectric. It is actual device. Yeah, you can see piezoelectric.
Other industrial applications. The whole presentation, both the last presentation for this session, is functional design of tall building by engineer Shiromal Fernando. Shiromal is the managing director of and principal structural engineer of civil and structural engineering construction private limited. high-rise buildings in the country, including the 350-meter Lotus Tower collapse. He holds the degrees of engineering, honors in civil engineering, and engineering degrees from the Infocomm. He is a chartered engineer of the Institute of Engineers in Lanka. As managing director, Shiromal Fernando currently leads civil and structural engineering consultants in private sector. Shiromal Fernando is the current chairman of IEEE Sri Lanka and the vice president of the Building Company of Sri Lanka in 2010.
Thank you, Professor. Good evening, everybody. I would like to first thank the organizers for inviting me. The topic that I'm going to discuss is very familiar to me and it's my job, designing tall buildings. So, in this presentation, I would give an introduction to tall buildings and some other aspects that we need to look at: the wind, earthquake, blast, and impact, the laws that we are going to consider during tall building design. Mainly, the lands are getting very expensive. The trend is to build tall, and basically, if you look at according to the CEng data, there are about 100 to 200 tall buildings, over 200 meters are built every year. Mainly, the country that leading tall buildings is China. Of course, like even in Sri Lanka, we have many tall buildings. To look at the skyline of Colombo skyline, it's amazingly changing. During the last 5-6 years, there are many tall buildings has been come to our. This is one of the completed structures during the last 2-3 years. With the introduction of this Port City project, for the next 20-30 years, we will have a lot of tall buildings to be designed. So, young graduates, undergraduates who want to become structural engineers, that's definitely a job for you. I have been involved in many tall buildings, all the tall buildings that have been done during the last 6-7 years. I have been one of the partners. So these are some of the buildings that I have designed, including the Lotus Tower, as Professor Lucas said, and he's also the electrical engineer of that project. And these are some of the projects. When you define a tall building, CEng gives the guideline. So generally, a tall building is a building that is more than 300 meters. And if it is more than 600 meters, we call it a super tall building. There are very few super tall buildings like Burj Khalifa. Now, Jeddah, there is a tower going on. With respect to Sri Lanka, in the 1950s, Selingo building was the tallest building that we had. A lot of people go to Colombo to see the Colombo through that. And later on, we got WBC. But we could not forget that our forefathers has built tall buildings 3,000 years ago. Tall buildings are not new to Sri Lankans. Jetavana Stupa, the tallest building structure today, has been built 3,000 years ago. And it was the second tallest building until, second only to the Giza pyramids, until the Eiffel Tower was built by the Frenchmen. So there's a huge tall building. The tall building is not a new thing to Sri Lankans. This is the first tall building in Manhattan, called Siga building. I think that is now over there. With respect to the tall buildings in the world, Burj Khalifa is the tallest building. It's around 800 meters. And when you look at the materials that have been used, if you go to the Empire State Building, mainly built in America, are with steel structures. And when you look at the buildings that are building in Asia and Saudi Arabia, are more with concrete material. And but now most of the tall buildings are built with composite, that is steel and concrete together. There are plans formed by the humans to build even 2.5 kilometer tall buildings. So there will be a lot of interesting challenges to the tall building designers. When you look at the tall building, it's like an inverter pendulum, a vibrating thing, and it's vibrating even without a force. So a professor has a good chance to put his potentiometer to generate. But the main challenge with the tall building designer is to control the vibration or the perception of vibration in the top stories. So this is, you can see it moves due to the wind or earthquake. So the sensitive people can feel the vibration on the top stories. So the main challenge that we have is to design so that people doesn't feel the vibration in the top floors. So basically, the wind is the main governing criteria when you design a tall building in Sri Lanka. The wind speed, now this is a wind speed that you get in a cyclone. So it's in the range of more than 100 kilometers per hour. You know the speed that we travel in the Southern Expressways is very fast, very high. These are cyclonic wind speeds. So cyclones are passing through us, especially in the northeast, every, let's say, 5 years or so. So we need to consider about cyclonic wind speed when we are designing tall buildings. So we have to look at the wind climate data. But most of the tall buildings are in Colombo, so actually the lowest wind speeds are in Colombo. Generally we design for about 38 meters per second wind speed in Colombo. These are some of the wind monitoring activities that we do in Colombo. This is it is actually published in our website. If you want to know the wind speed in Colombo at 200 meters, you can log into our website and see. So when you design tall buildings, we have different criteria. So especially accelerations, we cannot design for very high wind speeds, especially during a cyclone. Definitely the people on the top floors will feel. But when we are designing a tall building, we design for about 10 years period wind, like 30 meters per second. For deflections, we look at about 20 meters per second wind speed. When wind passes the structure, it will not only give a vertical like buffeting force, but also give we call it crosswind force because of the vortex shedding. You can see the next simulation, and you can see the vortices are forming, and there is it will form in the same period. It has a difference about 1 second. Because of that, the wind doesn't only push in the direction of the wind, but also it will move in the other direction. And also when it passes over the earth, it will also speed up, and it will have a larger effect on the top floors. It will have also a positive and also a negative impression for a tall building. And when you look at the wind effects at different levels, you will have different wind aspects. This is CFD simulation that done by us on a tall building. We normally cannot predict the wind forces mathematically. Therefore, we have to go for wind tunnel test to do get the wind pressures, the wind accelerations, and also the deflections of the building. These are some of the buildings that we normally, generally we control the deflections because the maximum deflection we normally allow is height over 400. And also we control the drift, interstory drift of the building because if your interstory drift is more than 2%, the windows will crack. So there are many techniques that we use to control the drift, the time to engage the perimeter beams with the core. So basically it's like a cantilever. These are called outriggers. The red color one are called outriggers. We're trying to fix all the perimeter columns also to the core. These are some of the structural, if you look at the CS tower, it is the bundle tube concept, and also the tower, the Hong Kong tower is about lattice truss. And then this is base tube concept. When you go taller, you have to use different structural system to control the drift and the deflection. If you look at this structures, which is the same location, the facade, shapes, the holes, the rim are used to reduce the wind forces to the structure. So one is called Shanghai Financial Center, Humankind Tower, and this is one of the new towers called Shanghai Tower, and you can see the different the shapes of the facade is to control the, and also pedestrian wind comfort is also very important. When you build a building, it's a big, huge monument where wind splash onto that, and that's a downflash water. Because of that, now we have found a lot of problems, like people cannot walk very close to the building because of this, our tall buildings. So we have to look at the pedestrian comfort. You can see the next slide. She's not doing a moonwalk. Actually, she cannot walk because of the wind effect due to the tall buildings around. So very dangerous. So this is a discussion about the earthquakes. A lot of people think we don't have earthquakes until the tsunami came to Sri Lanka in 2004. And this is IEEE point. Every day there are earthquakes in the world. Every time you can always look at it. And when you look at the Sri Lankan map, and Sri Lanka is the center of the plate. Most of the earthquakes happen around near to the plate. There are past history records that you have earthquake very close to Colombo, and there are geological geologists say there is a boundary very close to us, like 500 kilometers away. These are some of the records that we have. Very close earthquakes very close to Colombo. The first recorded earthquake is 1615 by the Portuguese. There have been many casualties. And in 1938 there have been many major earthquakes very close to the Colombo. So basically the earthquakes, when you design, this is called a cable grid. There is a subduction zone very close to Colombo. So there is a mainly this will be a hotspot that can happen. So if you have an earthquake, there is a big disaster. These are some of the cultural earthquake. See building collapsing, and basically tall buildings are very safe in earthquake. So due to earthquake, liquefaction can happen. If that happens, of course, your building will collapse. So basically, when we have an earthquake, the building will shake, and because of the inertia force, the top stories will have a lot of energy. So basically, what we need to make sure that it don't happen like this. Most of the time when we decide, we make sure that the hinges are formed in the beams, not in the column. So there are many guidelines by the Society of Structural Engineers to increase the ductility of the building. I will go through a little faster because basically by using the detailing we can increase the performance of the earth. Basically make sure most of the people die not because buildings falling, because most of the time it falls because of the walls are falling. These are some of the again we control the drift so that the damage is less. And fire is another issue which we have to look at. And the fire escape staircases, this is very close to, this is our office. There was a fire next door and we had to go through this thing. And these are some of the fire simulations that we have done for the Lotus Tower, how the people will go through. And this is actual fire this thing. And also the glass enclosure, this is called the robustness, very important in the Roman disaster. This place where gas, one element was dislodged and the whole part of the thing. And terrorist attack, the tall buildings are very vulnerable to terrorist attack because they want to do a statement, and because of that we need to look at those aspects also. Look at the events. Everywhere you have terrorist events, including Sri Lanka. These are some of the. When there is so we need to assess the stress, and especially when you are designing the building, whether there can be a car park or whether there can be when you design a car park, you need to design for a car park, or if it is an upper floor, there is a possibility explosive can take. This is a simulation in a car park. Again, this is a simulation that we have done for the Lotus Tower. We also have to design for impact loading, and this is also we have done for the Lotus Tower. So that if there is a plane crash, something like that. Thank you.
I will ask. Now, if we have 9/11 was just a few days ago.
Yes.
If we have a plane coming and striking the Lotus Tower, how would it withstand?
So what we have done is the Lotus Tower that was the upper floor is a steel structure. So what we have done is we have removed one steel member and try to find out what is the effect, whether the total building will fall into that, or as a tall building designer, what we are being guided is the whole building can come. So obviously that will be the effect on the affected area, but the whole system cannot come.
Presentation. So I'm just curious on the topic of smart buildings, because I know green buildings are there. I'm quite new to Sri Lanka, but I'm just asking whether smart building is kind of realistic in Sri Lankan context. And my second question is, to a degree you are married the concept of a smart building to smart cities.
Now, generally, we have a BMS system in the structure, which is going to monitor the energy and energy, and the water, etc. So that is the smart aspect that we can introduce to the buildings, and also you can have sensors so that there are no people to shut off and stuff. You can control and monitor. with respect to smart cities, then I don't so in smart cities, even the buildings communicate. Based on those things, I think we have a long way to go.
Any more questions?
In this lotus tower simulation, you said one steel frame was removed, panel was removed.
Yeah.
So, have you simulated what if it circulates that wasn't a panel that is supposed to be opened? Will that
One panel to be open already.
one of it?
Now, to look at this simulation, where we have like 225 kilogram explosive, and then and try to see what is going to happen to the column and the other panels. And if there is like a progressive collapse in the other but sometimes this can fall into the other lower and it can be erased back.
Any more? Okay, that's the artificial. Nalin, Jayakody, and he enlightened us on UAV-based green 5G communication. He told us about this. I did not really know that 5G was no different from 4G. I thought it was extension. He explained here to us that 5G is not just extension of 4G, but it's a completely different concept. Going from initially from maybe analog to digital, then to mobile, then broadband, and now Internet of Things, or massive Internet of Things, which is completely different from this mobile. The second talk was by Rear Admiral Simon Henley, Unlocking Space Access for Mankind, Reaction Engines and Stable Propulsion Systems. Again, I always thought rockets or whatever going to space had to go on. Till we talked about it, I did not realize that there could be something which is horizontal and then go on to outer space. And also that material used in rockets and rocket engines can be reusable so that even ordinary people in the future should be able to go to space and come back. And then of course we also talked about Sabre in a special type which will revolutionize space access for mankind. The third talk was on this design and fabrication of smart piezoelectric devices. Again, I did not realize that with our modern development, when we talk about smart, we think it's a term. But it's not a term. You are really doing something which will help something else. So with materials, I believe it's not directly, it will help. For example, even tall buildings and things for measurement, and I think you also mentioned about getting energy, harvesting energy, which I never thought about from materials. The final one was on Again, we think that tall buildings are tall. That's it. Of course, obviously it becomes more difficult to make. But the type of things that happen, even a fluidically movement, how it will affect a person on the top floor is something that we may not really think about. Then about how to escape in the case of a fire, how to consider effects of earthquake. For small buildings, I believe the effect of that may not be high. But when it's tall buildings, you are specifically designed to take all those into account, otherwise you are going to have disasters. So I think we had a very good session, and I thank all the authors for a very interesting session. Again, let us show our appreciation in the visual manner.
Thank you very much, Professor. That was such a scholarly discussion covering almost all the engineering sessions that we are studying so far. And I would like to thank again the speakers on behalf of the gathering here for the valuable knowledge they have provided us. Now, I have the honor of inviting Professor Rohan Lucas, accompanied by Dr. Matsuri Samarkon, Dean, Faculty of Engineering, to present the token of appreciation to our guest speakers. Professor Nalin Jayakody. Rear Admiral Simon Henley. Professor Shiromal Adikary. Engineer Shiromal Fernando. Thank you, sir. To present the token of appreciation to our chairperson today, Professor Joseph Rohan Lucas, may I now have the honor of inviting the Deputy Vice Chancellor, Defense and Administration of General Sir John Kutulawala Defense University, Brigadier Nanda Happusingha, accompanied by the Dean, Faculty of Engineering, Dr. Matsuri Samarkon, on stage. Ladies and gentlemen, it has been a privilege to share the knowledge in this moment with all of you among the intellectuals and learn from them. Time is flying. We all are under the rule of time, and every good thing must come to an end. Please remain seated. We have some more announcements to be made. You'll be accompanied to the FOE43 for your refreshments, and please be here in the same building, FOE42, for the poster session, post-evaluation session, starting from 16:30 hours. Thank you. With that, we'll be ending up today's plenary session. Thank you all for your honorable participation.